Oceanography class, this is a lecture on Animals of the Pelagic Environment, Chapter 14. Pelagic organisms, they live suspended in seawater, and they make up the majority of the ocean's biomass. Phytoplankton and other photosynthesizing microbes, they live in the upper sunlit surface waters, and they're the food source for nearly all other marine life. So all other pelagic organisms must remain or encompass the sunlit layers of the upper ocean. And so that means that they have to swim or they have to float. I don't know if you've treaded water before, but it's tough. So a lot of the marine animals have evolved specific functions to help them with buoyancy and avoid sinking. So one example is the use of gas containers. So the spirula, or the it's a type of cephalopod, or the nautilus, they have rigid gas containers. Okay, so those gas containers, they appear to look like a ram's horn right here. And this cutaway shows the shelled chambers in a nautilus. That can hold air, and that helps them remain buoyant. I don't know if you've ever seen cuttlefish, this right here, but these are amazing creatures that can adapt to like almost any color. They almost look alien-like, their tentacles. But they also have a cuttle bone that is a rigid container that holds gas and helps them keep buoyant. Other fish have swim bladders. All right, and swim bladders, there can be two types. One that's directly connected to the esophagus, and you'll see these fish kind of come up for air on the surface, and that's how they fill up their swim bladders. They can retain that air in their swim bladder. Sometimes if you're fishing and you reel in a fish too quickly, maybe like a swordfish or something, their swim bladders can kind of come out of their mouths, which is kind of gross. It must be very painful for them. And this allows for rapid buoyancy changes. If you can just go up to the surface and gulp some air through your esophagus right into your swim bladder, so then you can dive down or stay up at the surface. Other organisms, these adaptations specifically, their swim bladder is not connected to their esophagus, so it fills up with air only through blood vessels. Okay, and this allows for kind of slower buoyancy changes. But this is really helpful. I don't know if you've ever been scuba diving, but it's essentially like your BCD vest, and you can fill that up with air or let air come out of it, and that helps you adjust your buoyancy. Zooplankton a lot of times produce fats or oils, which are very low density, and that allows them to kind of float with expending the least amount of energy possible to kind of stay in those upper lit layers to kind of run into the phytoplankton. And then other organisms, or specifically nectonic organisms, they have to swim, and they have to keep moving in order to avoid sinking, and that can be quite tiresome, and that's why they've kind of evolved with their streamlined shapes to kind of keep them from sinking, and their fins to avoid drag and to provide lift. All right, here's a bioluminescent organism that lives in the deep. These floating zooplankton, they have shells that surround their bodies, and they're abundant in the deep ocean. They make up biogenous sediment. But the shells, they're called tests, and when they die, those tests kind of sink down to the bottom of the ocean. Here are some examples. Now these aren't zooplankton. This right here, these are diatoms, but they make their single-celled algae float around the surface of the ocean. But they make their shells out of silica, and those are those microscopic tests. These are all images from a scanning electron microscope, so these are really small. Yeah, there's no scale here. Sorry about that, but these are really small. Some of these floating zooplankton include Radial Aranes. These guys make their tests out of silica, and they come in a variety of really crazy ornate shapes for two reasons. One is to avoid sinking, so they have appendages that stick out, also to avoid predation. But the spikes that you see here help create more surface area and allows them to kind of remain buoyant. And radiolarians are single-celled protozoans. Here's some images. Foraminifera, these are microscopic, some are microscopic, some are macroscopic single-celled protozoans as well. Most foraminifera are planktonic, but the most diverse or number of species are benthic. So you can find these organisms in sediment at the seafloor. They produce a hard shell or test that's made of calcium carbonate, so that can dissolve away with some acid. And both the radiolarian and foraminiferan tests are common sea sediment or biogenous sediment. So these are floating and benthic zooplankton. Copepods. Copepods are microscopic shrimp, essentially. They're part of the Crustacea subphylum, and which includes shrimp, crab, and lobsters. Okay, so they kind of just basically look like miniature shrimp. They have a hard exoskeleton like those other organisms, and have a segmented body with jointed legs. Sometimes they have a forked tail as well. You can see the forked tail right here. There are over 7,500 species of copepods. That's a lot. And they have really special adaptations for filtering any kind of food particles from the water. Some of them are herbivores and only eat algae, and some are carnivores and eat other zooplankton that they run into. And some are parasitic as well. If you have 7,500 species, that means there's all kinds. They make up most of the ocean's zooplankton biomass. And all of these copepods, they lay eggs. And the eggs sometimes are carried attached to the abdomen, and then they're released into the seawater, and they hatch in about a day. And so that rapid reproduction allows great numbers of copepods to kind of live in those upper layers of the ocean. They're really numerous in the ocean, even though they're so small. They're numerically one of the most dominant types of multicellular organisms on the planet, and that's why they make great food for traveling whales into different oceans. Kind of swarm up and eat these when they're in their kind of mass swarms. Krill are an example of a macroscopic zooplankton. Okay, we can see them without the aid of a microscope. Krill in Norwegian means young fry of fish. Okay, so it's actually also a crustacea. So it's very similar to the copepod. There are about 1,500 species of krill, and the largest they get is about 2 inches long. They're abundant in Antarctica, and they're a critical portion of the food web there, and they supply food for a lot of organisms, from the largest whales to birds. Okay, you can see a bunch of dead ones kind of washing up ashore here. Here's a close-up view of it. All right, cnidarians are soft-bodied jellyfish, essentially, with stinging tentacles. They're 95% water, and the portion of their tentacles that stings, they're called nematocysts. And Cnidarians fall into two basic groups. One is hydrozoan. The Portuguese man o' war is a great example of this. I don't know if you've ever seen this, but sometimes if you go to the beach, they'll hold up a purple flag and let you know that there's jellyfish in the water, and occasionally you can see these man o' war jellyfish, and essentially they're kind of like purple gas-filled chambers sit on the ocean surface, and they basically get pushed around with the wind, so they act like sails to move around, and then their tentacles are like 20 feet long, and if it stings you, it really, really hurts. So I think the next slide has an image of it. And the next group is the Symphozoan, or just the jellyfish or jellies. These are Cnidarians as well. They have a bell-shaped body and a fringe of tentacles, the mouth at the end of it, and it's beneath their bell-shaped float, and then they kind of grab organisms and pull it into their mouth. Okay, they can range in size from microscopic to about 6.5 feet. Okay, but most of them are small, less than 0.5 or 1.6 feet in diameter. So the way they move is by muscular contraction within their bell. So water enters the cavity and then is forced out. And I'm sure you can imagine, let's see the next image, I think we have some, yeah, you can see they kind of suck in water and then push it out. They contract and expand, and that's how they kind of just float around in the water. Here's a Medusa, and this is that Portuguese man o' war. This is what they use as like a sail, so to speak, is so when wind is blowing, it kind of can push it in different directions. All right, and these are those really long stinging cells. All right, let's talk about swimming organisms or nectonic organisms. This includes fish, squid, sea turtles, marine mammals. There's some interesting forms of organisms that swim. The flying squid that you see pictured there, they move by trapped water in their mantle cavity, and it kind of shoots out, and then they jump out of the water. Basically it's like propulsion, and the water is siphoned out, and they kind of fly around like that. Other organisms, they swim by curving their body from front to back. The fin designs are crucial for fish. Each fin plays a different role. Okay, the paired vertical fins act as stabilizers. The pelvic and pectoral fins are for steering and balance. The tail fin here is mostly for thrust. And then there's sometimes you'll see, oh, it's right there, the lateral lines right here. It has a network of sensors to detect pressure changes, which is very important because that lets you know where you are in the water column. If you're in very shallow water, here's that lateral line, or the dorsal fins, the caudal fin for thrust, anal fin for steering, pectoral fin also for thrust and stabilization, and here are the pelvic fins. So swimming in the water with the fins can differ from organism to organism, and it's just contraction and relaxation of different fins in the body, and there's a lot of different motions. There's thunniform motion, which that's a lot of predators have that, where the caudal fin provides a lot of the power. Then there's the omniform, which is what you see here. I don't know if you can see, look closely over here. See that fin back there? It's almost like as if it's like a hummingbird, but that's that kind of S motion in the fin, and that keeps the seahorse kind of up. All right, let's see some other examples. I think here, yeah, here we go. Here's the caudal fin to provide that power to go through huge breadths of the ocean, different areas, and also at different pressures or depth. Here's the amniform. Labriform are, this is the parrotfish, and it's sculling with the pectoral fins. And then if you see a sunfish, this kind of flat fish here, this is the ostraciform, and this helps the sunfish kind of approach and kind of like skim the water essentially. So the sunfish can kind of almost like float to different areas and turn to its side. And this is that kind of range of motion back and forth, which is a little different. There are also rounded caudal fins. All right, you see that here. That makes it really flexible, which is great for maneuvering at slow speeds. Here, flounder has that, or a sculpin. Here's a blue-faced angel. This helps to be maneuverable in an environment where there are a lot of rocks, holes, and crevices. So if you see a predator, you can quickly maneuver into one of those and be safe. That's why that's helpful. Sometimes you'll see truncate or forked fins. Here's a forked fin right here. That's useful for maneuvering and thrust. If you have a longer upper forked fin, that helps with lift, so you don't sink into the water as much. All right, so that's true of sharks. Sharks will have a large upper caudal fin there. We refer to that as lunate fins. And they're very rigid, so they're less maneuverable, but they're very efficient at propulsion, and they're fast swimmers. Tuna, marlin, and swordfish are kind of like that. Okay, that they have the bottom part of the caudal fin is larger, and so I don't know if you've ever seen swordfish are really fast, and so they kind of just scream right through the water for very short, quick bursts to get their prey. Heterocircle fins are asymmetrical, and that's what I was highlighting here with the shark. This just helps, so like if a shark, the idea here is with wild organisms, they want to expend the least amount of energy because they don't know when they're going to get their next meal. So with a shark, they can kind of cruise in the water and not have to worry about keeping themselves up in the water column because their fins provide lift. So much like an airplane kind of flying through the air, the wings are designed to help keep the airplane in the air, or like gliders, helps them float up, so they use the least amount of energy as possible. Now there are other adaptations for predators to find prey. There's two main kind of strategies here. There are lungers and cruisers. Lungers, like you see here, wait for their prey and then pounce. Groupers do that, and as a result, their muscle tissue is white. Cruisers are ones that actively seek their prey, and so they have to be swimming all the time, and their red or their muscle tissue is mainly red. And we'll talk about why. So here's a grouper if you've never seen one. Groupers are also often commercially available to eat. It has kind of a white meat. And then cruisers here, this is a yellowfin tuna, also commercially available to eat and very delicious. And tuna will hunt in these huge packs like this, and they move fairly quickly, and they kind of move quickly and swiftly through the water. They're top predators. So there's a difference between lungers and cruisers in terms of their muscle tissue. There's red versus white. Red muscle tissue, you have small fibers as in comparison to white. So cruisers have much more red tissue, and you can see that this is tuna just cut wide open or filleted, so you can see that. Delicious, right? And so with cruisers, much like tuna, what they have are high concentrations of myoglobin, and that's a red pigment, and that has a lot of oxygen affinity, so it makes them it supplies more oxygen more efficiently to their muscles, gives them a higher metabolic rate, and that's why tuna have such great endurance to be swimming and cruising around in the open ocean. Lungers, on the other hand, this is a fillet of grouper. They have little red tissue, and that's because the lack of continuous movement. White tissue has less myoglobin, and it fatigues more rapidly, but that's fine because they just need quick bursts of speed to kind of capture their prey. Another adaptation for finding prey is swimming speed, and here's a good example of a swordfish kind of cutting through the water really quickly. And speed is generally proportional to size, so a lot of fish can move very fast, but for a very short period of time. And a lot of the fish that move really quickly, it's really just to elude prey. Most fish are cold-blooded. That means they're poikilothermic. That means their bodies are really the same temperature as the environment, and those are typically not fast swimmers. Other typically predators are homeothermic, which means they're warm-blooded. They're found typically in warmer environments, and that warm-bloodedness or keeping them warmer than the surrounding water helps them capture their prey. It makes them more efficient swimmers. Now, if we look at deep, oh God, look at that. Yep, that'll haunt you at night. You can't unsee that. Thanks, Professor Holbeck. But there are deep water nectin. So think of the anglerfish. That's an anglerfish there. And these fish, with the exception of the anglerfish, it's, you know, sensationalization. I like to wow you with some of those cool pictures. But these fish that live in deep waters and perpetual darkness, they typically consume detritus, which is just small morsels of food that just happen to kind of fall through the water column, and they filter feed. So there's a lack of abundant food at these levels. Okay, there's kind of like there's not a lot of, life is very sparse in these areas. And so one of the cool adaptations that deep water nectin have or use or adapted to, or, you know, just essentially evolved to having, is bioluminescence. And bioluminescence is essentially they generate light. They contain, their cells contain photophores, and that generates light. And they do that for a number of reasons. One, to attract prey, like the anglerfish will kind of hang a light in front of its mouth, and so unsuspecting prey will be like, oh, that's so pretty, and then it just gulps it up. And the other is actually to attract other fish of the same species, so you can reproduce. It gets kind of lonely in the eternal darkness of the deep ocean. So, you know, everyone deserves somebody, right? Click on that YouTube video, and you'll find really cool bioluminescent algae that's crashing on the waves in Puerto Rico or something. It's kind of beautiful. So typically, deep water nectin, God, another image that's just haunting. But they have large and very sensitive eyes. Obviously, they have to be very sensitive because they're in complete darkness, so any little bit of bioluminescence or light that they see down there, they could track down and hopefully find a mate or some food. Large, sharp teeth, we've seen that. Expandable jaws, and a giant belly to hold so they can eat whatever they find in one big gulp, because food is very scarce there. So when they find a meal, they're going to eat, like, completely eat it up, and then that'll hopefully, you know, fill them up for, you know, a month or two if they don't find any other food. And they have hinged jaws, right? So they can unhinge their jaws to fit something almost bigger than them inside of them, inside of the anglerfish, which is pretty crazy. Yeah. So here are some more examples. Here's the hatchetfish. You can see its giant eyes. Lanternfish, again, big eyes in comparison to its body, in comparison to more shallow water fish. Here's the gulper eel. Look at that mouth. That's ridiculous. Okay. And then here are the anglerfish. All right, here are the scales. This is 10 centimeters or 4 inches. So anglerfish are pretty big, okay, or can be pretty big. Here's how they unhinge their jaws to fit an entire fish into that gullet. So here's an example of the ingestion of this species of deep water nectin. Okay, other adaptations that fish use to avoid predation or schooling. That's the idea of safety in numbers. Kind of like herds and you know, mammals and grasslands and stuff like that. It's essentially like you would think in the ocean. You know, there's nowhere to hide, right? So if you form a school and kind of maneuver around in circles and try to confuse the predator, because it's kind of hard to pick one of you guys out from the entire school of fish. And also, it appears larger as when you're all together than as a single fish that could scare predators away. And the maneuvers kind of help confuse the predator, and so it helps these smaller fish kind of strengthen numbers, so to speak. The cool thing about a lot of marine organisms is that a lot of them kind of depend on each other or can develop relationships of mutual benefit. We call this symbiosis. So that's either two or more organisms that they mutually benefit from their association. One type of symbiotic relationship is commensalism, and that's when a less dominant organism benefits without really harming a host. And with shark and remora fish will kind of just latch on, and they just feed on the scraps from when the shark bites something, and ultimately some detritus kind of flies out, and they come in and swoop in and eat on that. And they're very aerodynamic, so they can kind of, they don't affect the drag of the moving shark. They can kind of stick underneath it. Mutualism is when both organisms benefit. And the best example, or a good example of this, is a clownfish and anemone. The clownfish has evolved in a way that they're not affected by the stinging nematosis from an anemone. And so that provides a really safe environment because predators don't want to mess with stinging nematosis, right? So they don't want to go near that environment. And on top of that, so then the clownfish, the way it helps out the sea anemone is that it keeps it clean. It'll clean off all the sediment covering it, so that the anemone remains kind of viable and clean and can survive easier with that relationship. And then the last kind of symbiotic relationship is one that doesn't help both partners. It's called parasitism, and a parasite benefits at the expense of a host. So here, this is an example of one. This isopod has attached itself to the head of this soldier fish, and it's essentially extracting nutrients for its own benefit, and this guy's got a giant zit on his head and can't do anything about it. All right, let's take a look at some of the marine mammals. They're mammals. They're just like us. They're warm-blooded. They breathe air. They have hair, okay, or fur. They bear live young like we do, and they have mammary glands for milk. So we're in the same family as these marine organisms. That's pretty crazy to think of how mammals kind of evolved and found their ways into the oceans. They believe the kind of starter species, or the closest related, mammal species that eventually evolved and moved into the ocean, were elephant or hippopotamus-like organisms that were in shallow waters for a while, and then slowly they evolved to have stream-like bodies and venture out into the ocean, and then those species evolved to all the different types of whales. But that's pretty crazy to think of how long that took. But here are the major mammal groups. Okay, so here's the marine mammals, class Mammalia. So we've got carnivora, and that includes sea otters, polar bears, pinnipeds, and pinnipeds include seals, walruses, and sea lions and fur seals. The order Sirena, okay, that includes manatees and the Southeast Asian version of a manatee, or a dugong. And then we have the cetaceans, and cetaceans are the different whales and dolphins. Okay, we have cetaceans that are toothed, so toothed whales, that include sperm whales, dolphins, and porpoises. And then the mustached whales, which are the blue whale, finback whale, right whale, humpback whale, and gray whale. So let's talk about the pinnipeds. They have prominent canine teeth. So sea otters, polar bears, walruses, seals, fur seals, and sea lions. Wow, I just kind of bunched those together. Those are part of the order Carnivora. Sea otters are crazy. They're pretty cool. They live in places where there are kelp beds or kelp forests. So these areas are where this kind of protist kind of grows from the sea floor upwards and photosynthesizes, and it provides a kind of a really cool environment where the sea otter can kind of move around in. It's typically in the North Pacific, so it's very cold water. Sea otters have very dense fur, and they're not like other organisms in the order Carnivora, meaning they don't have a lot of blubber, so that fur is really thick, and it was highly sought after early on in American history, and they're almost kind of driven to extinction because of the fur trade. But they're pretty incredible. They'll float on their backs. They'll have their young who aren't that good at swimming, and they'll put them on their bellies and float on their backs. They'll be seen holding hands, floating together. Pretty cute. And they have a really a lot of variety in their diet. They'll eat clams, they'll eat sea urchins, all kinds of stuff that's marine organisms that are found around kelp beds. And they eat a lot, and they're almost like ocean beavers, let's say. Okay, and they've been known to use tools, so they're pretty smart. All right, polar bears, you guys know this. They have the massive web paws. These guys are bigger than grizzly bears. They're huge. They can be like 12 feet tall. Imagine a polar bear just standing up on its hind legs, and it's 2 feet taller than the top of a basketball hoop. That's excessive. They're excellent swimmers. They have to be, because they typically live in areas where there's sea ice, and sometimes there can be large spaces in between sea ice, so they have to swim long distances. They have thick fur. Their hair is hollow. If you shave a polar bear, they're black underneath. Their skin's kind of black. They just have white hair, and they mostly eat seals, the earless seals. Right? And then there are walruses. Look at these guys, big boy, right? Large bodies. They all have ivory tusks, and they were also hunted because for their ivory. They use that for fighting and protection, and also I imagine to help climb up little pieces of sea ice as well. All right, very, very huge blubber-filled bodies. They can weigh a lot. Okay, and then here are seals. Seals, there are two different types: earless seals and true seals. Okay, harbor seals are here on the left. This is what polar bears eat. Yeah, I know, they're so cute. And they kind of do, like, you ever seen the dance move where they do the worm? Yeah, that's how they kind of move on ice or on land or something. So that's when they get hunted by polar bears, when they're kind of stuck on land or on sea ice. In the water, they're much quicker, and so they can evade polar bears that way if they get in the water. And if you've ever been to California or San Francisco, San Francisco, and you go to the Bay Area or the harbor, where the docks are, you'll see a lot of these California sea lions over here, and they have their body shape is a little different. Okay, get into details here. So seals lack kind of prominent ear flaps, and they have smaller front flippers. Okay, so here's that seal right here, and so their hip is shaped a little different. It's a little flatter and smaller front flippers. Okay. But again, same hip and hip shape or design as humans, and same the shoulder blade, which is pretty crazy. And then the different hip structure of the sea lion, you can see that here. They're kind of broader on their chest. They kind of stand up differently. They walk a little different. Well, I wouldn't say walk, but shift side to side. And so they have different locomotion strategies, and that's because they go after different organisms. They live in completely different environments, so the strategies are different. All right, let's talk about the order Sirena, which includes dugongs and manatees. These are herbivores, and they're in the shallow coastal grasses. I'm sure you guys have seen manatees in Central Florida. I saw a lot at Blue Springs State Park, which was kind of nice. I went there over the winter break, not too far away, and you get to see a lot of them. They kind of come inland to enjoy the warmer waters in the wintertime that are coming from the springs. But manatees are found in the areas of the Atlantic Ocean, they can grow up to 14 feet and weigh more than 3,000 pounds. It's a big boy. Okay, dugongs are found in the Indian and Western Pacific Oceans. Let me show you pictures so you can see the difference. I'm sure you're familiar with these guys. They kind of have that caudal fin that isn't truncated. Okay, and then here's a dugong. You can kind of imagine, you know, like these guys are closely related to elephants. Elephants spending a little too much time in the water, enjoying some of the high productivity in maybe shallow coastal waters or something. And then they kind of slowly evolved into dugongs and manatees. All right, let's talk about cetaceans. These are whales, dolphins, and porpoises. They have an elongated skull and blowholes on the top of their skull. They have very few hair, and they have a fluke, which is a horizontal tail fin, and it's great for vertical propulsion. Excuse me. Okay, and some of these guys are huge. All right, here's a blue whale. This thing is the most massive animal in the ocean. Okay, and it's essentially 3 school buses parked back to back to back. That's how big they are. There's a killer whale. Okay, here's a right whale. I have some pictures of that. Here's a sperm whale. They dive pretty deep, and they look pretty crazy when they dive. Here's a gray whale. Feeds on a lot of benthic organisms at the seafloor. Your bottlenose dolphin, and different species of dolphin. And here's a diver just to show you some scale. That would be you under the water. Okay, so they have a bunch of adaptations to increase their swimming speed. Again, they're mostly predators. They have very streamlined bodies. Look at these dolphins chasing after a boat. I think someone put their camera just under the water like a GoPro or something. But their skin structure is 80% water. It has a stiff inner layer. And if you've ever pet a dolphin, you can kind of feel like they're smooth in one direction. If you go with the opposite direction, it feels like, it's like really hard. So they definitely have like aerodynamic skin structure. And it's narrow canals with these kind of spongy material. And they also have adaptations for deep diving. They can absorb oxygen very efficiently. So with a sperm whale, as an example, they go down into really deep waters, like farther than light can reach. So they kind of dive in complete darkness. But they'll go up and breathe at the surface for a while, intake as much oxygen as they can. They're able to absorb about 90% of the oxygen inhaled. In comparison, humans are around the 20 and 30%. All right, and the other thing is they're able to store large quantities of oxygen in their blood. And then they're able to reduce oxygen use in their body by shutting down non-critical organs. Like they can be like, spleen, I'm not going to use you for a while. We're going for a deep dive. And that can happen. And their lungs are also collapsible too. So as they take huge breaths and then dive down, they collapse their lungs as they go into higher and higher pressures, which is pretty crazy. The muscles are insensitive to buildup of carbon dioxide, unlike ours. Their lungs are collapsible, and they alveoli, those tiny chambers, they facilitate the gas exchange with the blood, and that's why they're so efficient at delivering oxygen from their lungs to the bloodstream, essentially. So here's that nasal opening or the blowhole, the trachea right into their alveoli. So they still, like a lot of whales or cetaceans, when they dive deep, they can still be affected by the increased pressure from deep diving, but the debilitating effects are minimized. Think of it in terms of evolution. The whales that were able to dive down or had special adaptations to withstand deeper waters were able to get more food, kind of getting those DSL organisms that are nocturnal in the dark, deep waters, like squid, jellyfish, as an example. They are successful and go down and eat them, and they're because of their special adaptations. So they're able to reproduce and have children to pass on those special adaptations, and that kind of move forward and pushes the kind of evolutionary success of those organisms. But they can still suffer from nitrogen narcosis. Humans get that when they're diving in for prolonged periods of time in really deep water. And essentially what happens is you get the bends or decompression sickness, and you'll get actual nitrogen bubbles in your blood that kind of come out and burst if you resurface too quickly. That can cause bone damage, excruciating pain, and possible death. A lot of people, especially like fishermen in Indonesia and stuff like that, a lot of times they put themselves at risk to dive deep and find benthic organisms, for profit, to make money as their livelihood. And the more they get, the more money they'll make, but they put their bodies at risk from being in such deep waters. And the deeper you go, the more fish you find. So they take these big risks, and they can suffer, they can have brain damage from this, because these nitrogen bubbles can kind of expand while in your brain. Okay, and some people have died as a result of it. Okay, a suborder of cetaceans are the toothed whales. That includes dolphins, porpoises, killer whales, and sperm whales. And what's cool is that they can use echolocation, right? And that helps determine the distance and direction to certain objects, mainly prey. They can use it to identify other organisms, but it helps determine the shape and size of objects. Okay, porpoises are different from dolphins. Oh, look at that thing. They're smaller, they're more stout. They have a blunt stout, you can see there. Pushing their stout down. And a smaller dorsal fin and blunt or flat teeth. All right, dolphins are larger, they're more streamlined. They have a longer kind of nose, okay? And their dorsal fin can sometimes be hooked. And they have pointy teeth like killer whales. You can see that someone's holding the jawbone of one. But echolocation is pretty cool. Like, essentially, it's like it's another organ. You know how like we have eyes and ears, and that helps us identify things in our environment, right? So like we can see things in color, we can hear things from far away. But these organisms have evolved an organ in their body, in the front of their heads, and they generate a sound or a frequency from this organ. And then that travels out in front of them, right? And it hits these fish and is reflected back, and they can receive that information and use that information to identify even the species, right? So like a dolphin pod can be like and do their echolocation and be like, oh yeah, there's some tuna up ahead. I haven't had tuna in weeks. Let's go in this direction. We found a pod of tuna. Let's go hunt them. Okay. So they emit those sounds from their blowhole. It passes through the melon. That's that organ that I was just referring to. And it's an organ in the skull. Okay. And they can determine even the type of species based on the reflection of those sound waves off the species and reflected back to them. Okay. They send the sound through the water, and they have a different inner ear structure to help pick up those sounds. And some of the whales, like the sperm whale, they force the air through a nasal passage. Okay, and that's through the spermaceti organ. We'll show you a cross section of the sperm whale. Don't worry, I knew you wanted to see that. But here it is. Here's the blowhole. I'm sorry. Here's the blowhole. This is where they generate the noise. The nasal passage here. Sperm whales make like a clicking sound, like a click, 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 click. And the more clicks they make, the closer they are to an object, because they want to know if it's moving. They want to see the reflections coming back. And then as the reflection kind of comes back, here goes the noise. And as the reflection comes back, it goes and feeds into their brains, and then they know which way to go. And that's how they find squid and jellyfish. And these guys are incredible. You should watch. I'm pretty sure on the My Media page I posted BBC Blue Planet 2 videos of pelagic organisms in the open ocean, and they show sperm whales kind of just like hanging out in the middle of the ocean and then making deep dives in the darkness, which is pretty cool. And then here's the dolphin. Here's the blowhole. Here's the melon that generates the noise, and then the reflection comes back, hits the bottom of their jawbone, and travels up to their ear, and then they can decipher, oh yeah, this species of fish, let's go. That's pretty cool. All right, so they can determine exactly which fish they want to eat. All right, and the problem is since we have a lot of ships out in sea, they may create a lot of noise that might disrupt the echolocation hearing, so to speak, that they use. If we've got loud boats, or if we've got the use of seismic waves or explosions in the ocean, or high frequency sounds that the Navy uses. Those sounds can be detrimental to cetaceans out in the ocean. Sometimes it drives them. Sometimes those high frequency noises, a lot of times the Navy uses experimentally to for different purposes, but sometimes it drives whales to beach themselves on land, which is not a good thing. Okay, so toothed whales are very smart. They have very large brains in proportion to their body size, and they can also, not only can they use that melon and echolocation to find prey, but they also use it for communication. So they have highly convoluted brains. That means they form complex relationships social relationships with other cetaceans, and they travel in pods, so they communicate pretty well. And so they're trainable, as you know. I'm sure maybe you've been to SeaWorld. Wild dolphins have been known to assist drowning humans, right? How would they know that? That means they understand compassion and helping another organism out. So that's pretty cool. That's pretty smart. All right, then there's another order of cetaceans called the Mysticeti, which includes baleen whales, blue whales, finback whales, humpback whales, gray whales, and right whales. And what they have are fibrous plates that sieve their prey items. And so typically what they're going after is different species of zooplankton. And again, they can vocalize sounds for various reasons to find out, lost loved ones out there, or mates, or other pods, which is pretty cool. So here it is. Here's the cross-sectional view of a baleen whale. Here are those baleen plates. Okay, so they gulp in a lot of water, and then they press their mouths closed. And then if there are any organisms in that water, they get stuck in between the baleen plates, and they push out all the water. And then it becomes food, and they just gulp that down. All right, so they fill their mouths with water. They trap fish, krill, or plankton. Oh yeah, see here? Krill goes in, squish, water goes out, krill stays in there. Yummy. All right, here's a picture of some baleen whale teeth right here. Right, and look, just for scale, she's holding one. That's huge. Okay, so here are the different families. Gray whales are short, coarse. They have no dorsal fin. This is one right here. They're on mostly on the west coast, off the coast of California, on the Pacific Northwest. Okay, they're bottom feeders, so they jump down to the bottom of the ocean and just kind of scrape up benthic organisms. Right whales are longer. They have very fine baleen and no dorsal fin. This is one pictured here. They're in the North Atlantic and the North Pacific. And right whales are the most critically endangered whales in the world. All right. Then there are rorqual whales. They're the baleen-pterids, which are long and slender-bodied. And then the megapterids. This is one of those. Those are the humpback whales. All right, humpback whales are pretty cool because this is what they'll do. This is pretty cool. They come in kind of groups, and they feed at the surface by creating a bubble net. So they go into, so say there's a lot of krill or zooplankton in the water, copepods or something, and then so they create, see this, a spiral of bubbles. And what the bubbles do is that it pushes all the krill closer together so that they're like more concentrated in the water. And then as they kind of corral them together and really close, they all come up at the same time, boom, and then just swallow up all the water where that concentration of krill is, so that it, and they come up in the center of it. So they huge bubble circles, and then the center is where all the krill are, and then they come up from underneath, gulp them all up, which is pretty cool. It's pretty smart, honestly. Here's an example of gray whale migration. Okay, gray whales, they travel over 22,000 kilometers every year. Okay, and so they go from the coastal Arctic Ocean in the summer, right, to feed on the great primary productivity that occurs in the Arctic summers, and then they make it all the way down to Baja California in the Gulf, right next to Mexico here, during the winter. And they do this every year, essentially There is a smaller group, the Pacific feeding group, that don't make it all the way down to the Gulf of California here. But a lot of them make it all the way down here. They go down here because this is when they give birth to calves. And so they're in warmer waters. There is some food here as well. So, and then they take their calves up, take advantage of the temperate feeding that goes around here in temperate open oceans, right? Productivity in the spring and fall. And then in the summer, they feast on the buffets up here. Okay, which is pretty crazy. And they do this on a yearly basis. So they have a calf, they bring that calf all the way up through this entire migration, and then they're like, peace, you know, and then they do it next year. Imagine having a kid every single year going on a 2,000 to 22,000 kilometer migration and then saying goodbye. You're on your own. That'd be nice. Anyways, but they're pretty quite crazy. Gray whales, and it's crazy too, killer whales will hunt the calves of gray whales. That's a terrible killer whale. Okay, don't know how to draw. And you know what's crazy? Killer whales are like the apex hunters of the ocean. They'll kill and tire out the calves of gray whales just to eat their tongues. So they have a very specific palate, and they'll kill the calves just for one organ, which is crazy. So the gray whales feed in the Arctic during the summer. They breed birthing grounds in the tropical eastern Pacific, so in the winter. Okay. And so most of those gray whales migrate. About 200 stay along the Pacific coast. And they take advantage of that coastal upwelling, which is typical of the coast of California. Okay, so whales are endangered species. Okay, there are fewer whales now than before whaling. And so that was a big issue. So the International Whaling Treaty was signed amongst many different countries. Hunting gray whale was completely banned in 1938. If you look at gray whale here, this is their pre-whaling population, and this is their present population. So gray whales have kind of made a good comeback, but they're still there aren't too many of them. Okay. They've been removed from the endangered species list in 1993 as that population rebounded. But still, right whales are the most affected here. These are the right whales. They used to have populations greater than 100,000, and now there's less than, or just above 1,000 of them. Blue whales also, most of the whale populations are much lower than they used to be. Okay. Right, and gray whales show friendly behavior. You can go up in the boat. Look, this guy's actually touching one. And the International Whaling Commission was established in 1948 to manage whale hunting. And in 1986, 72 of those nations in that commission banned whaling altogether. So there's only 3 ways to legally hunt whales. One is if there's a complete objection to the ban, or if there's scientific whaling, or aboriginal sustenance whaling. And that's there are a few cultures in Indonesia that they'll go out on canoes and hunt one whale for the season, and that would provide food for the entire kind of village. They still allow that because that's not like greed and hunting as many whales as possible for profit. That's just for sustenance for a group of people. But it's difficult to tell certain cultures, like Japanese culture or Norwegian culture, which have whaled for hundreds of years, to tell them that, hey, no, you can't do what you guys have been doing for all that time. But still, it has to be understood that if you continue whaling at our efficient ways, you won't have a rebound in the population of certain species of whales. So there might not be whales in the future if this continues. So there's still a lot of controversy and fighting over what whaling is allowed, or because it's really hard to enforce in the open ocean and on international waters.